Hello everyone, welcome to my YouTube channel MechE-FUNdaMENTALs. In this video, the topic is static equilibrium. In the series of Fundamental of Mechanical Engineering, the topic is static equilibrium, in which I will discuss the equations of static equilibrium, free body diagram, types of support reactions, types of loading, and the free body diagram of a vane and support reactions. So first, what is static equilibrium? So body is at rest under the action of any force system is called as the condition of static equilibrium. Now you see in this diagram, a weight is in the rest condition, and to make it rest we are applying a force F in the other end of the string, and that weight is supported by the pulley and the string. So this is the condition of static equilibrium because the whole system is under equilibrium, and definitely the weight is also under equilibrium. And for a body to be in static equilibrium, all the possible movements, which is also known as the degree of freedom, must be adequately restrained. And what is the meaning of degree of freedom? It is the number of independent parameters required to specify the state of an object. Or we can say that the degree of freedom is actually the independent basic ways about the body can move. Now, the degree of freedom we talk about with respect to the force system. Now, the first one, that is a non-coplanar force system, which is also called as three-dimensional force system. And in that, a rigid body has 6 degrees of freedom. 3 translations, that is x, y, z, and 3 rotations, theta x, theta y, and theta z. So here you see this is the body in the three-dimensional force system. So the number of basic ways this body can move, that is translate about x direction, it can translate about y direction, it can translate about z direction. So we have the 3 translation about x, y, and z. So these are the 3 degrees of freedom in terms of the translation. And we have the 3 rotations. That is the first one, that is the rotation about x-axis. The second is that is the rotation about y-axis, and the third, that is the rotation about z-axis. So in non-coplanar force system, 6 degrees of freedom, 3 in terms of the translation along x, y, and z, and 3 rotations about x-axis, y-axis, and z-axis. And now we see the coplanar force system. And when we talk about the coplanar force system, so first we talk about with respect to the rigid body. So in the rigid body, we have the 3 degrees of freedom, 2 translation about x and y, and 1 rotation about the z-axis. You see this diagram. Coplanar means all the forces are in a plane, and this is the body. So the independent basic ways this body can move, that is first, that is the translation about x direction. You can translate about y direction, and it can rotate about the z axis, if you see like this. So we have the 3 degrees of freedom, 2 in terms of the translation about x and y, 1 is the rotation about the z axis. If in the coplanar force system there is a particle, then we have the 2 degrees of freedom. It means we have the 2 translation x and y. You see this is the point. So it can translate about x direction, it can translate about y direction, and there is no rotation with respect to that particle. So we have the 2 degrees of freedom in terms of the translation about x and y. Now the equations of static equilibrium. So first we talk about for a non-covalent force system or the 3-dimensional force system. As I already discussed the degree of freedom for a non-covalent force system, we have the 6 degrees of freedom, that is translation about x, translation about y, and translation about z. And we have the 3 rotations, theta x about x-axis, theta y, that is the rotation about y-axis, and this is the rotation about z-axis, that is theta z. And now when we talk about the equilibrium, static equilibrium, then the equation we can frame out with have the degree of freedom, because when the body is under equilibrium, then all 6 degrees of freedom must restrain. Then only we can set that is under static equilibrium. So to make that body under static equilibrium, the first one, that is the net horizontal, that net force along the x direction is 0. And when the net x direction force is 0, it means there is no translation about x direction. The next equation, that is the net vertical force or the net y direction force, is 0. It means there is no translation about y direction. The third is the net force along the z direction is 0. It means there is no translation about z direction. So if we have net x direction force 0, net y direction force 0, and the net z direction force 0, it means we freeze or we restrain all the three translation of that body. And now about the rotation. If the net moment about the x-axis is 0, the net moment about y-axis is 0, the net moment about z-axis is 0, it means we restrained all the three rotation also. So the equations of static equilibrium for a non-covalent force system means we restrain it all 60 degrees of freedom. So we have 6 equations: net x direction force 0, net y direction force 0, net z direction force 0, as well as to restrain the rotation, we have the net moment about the x-axis is 0, the net moment about y-axis is 0, and the net moment about z-axis is 0. And now we talk about for a covalent force system. Now if it is a rigid body means that will coplanar non-concurrent force system. And I already discussed that we have the 3 degrees of freedom in the case of the rigid body under coplanar force system. Then if that body is under equilibrium, then all the 3 degrees of freedom must restrained. It means the net force along the x direction is 0, which will restrain it x direction translation. The second is the net vertical force or the net y direction force is 0. It means that will restrain it y direction translation. And the third one, that is the moment about any point on that plane about the z-axis, that is also 0. So we have the 3 equations. If that is a rigid body, it means that is a coplanar non-concurrent force system. If there is a particle, it means that is a coplanar concurrent force system, and it has 2 degrees of freedom. And to be in static equilibrium, then both the degree of freedom must restrained. It means the net x direction force is equal to 0 and the net y direction force is equal to 0. Then only that particular particle will be in static equilibrium. Now the free body diagram. So the free body diagram is actually an approach to solve the numericals or the problems of the static equilibrium. So when we define the free body diagram, so free body diagram is the diagrammatic presentation of any body which is isolated from its surrounding, and all the forces mean applied force, body weight, and the support reaction that we have to draw on in it. So that is known as the free body diagram. You see in this particular example, this is a weight Wmg which is supported by the 2 string like this, and this particular body is at rest. So now we draw its free body diagram. So this is the body. First we have to isolate it. This is the isolation. Isolation means we have to remove the supports actually. So here we have the 2 string in the support. So we have to remove these supports. It means we have to isolate that body from its surrounding, and then we have to draw all the forces. All the forces mean the applied force, the body weight, that is mg, and the support reaction. So both the string will support it by some reaction, and in the string the reaction that is in the form of the tension. So in the first string, that support reaction that is in the form of the tension, that is suppose that is T1, and the second string also give the support in terms of the tension, that is suppose that is T2. So now we present all the forces in that particular isolated body and we label the diagram. So this is the free body diagram, and that is an approach to solve the numericals or the problems of the static equilibrium. If you see the steps involved for free body diagram, so here we have the major 4 steps. The first one is we have to select an isolate of an object. This is the body whose free body diagram we have to draw. So first we have to isolate it. It means we have to free from its surrounding. It means that is both the strings. So select and isolate an object. Body to be analyzed must be free from the support. Supports means the surroundings. Second one, identify all loads. All loads means that is the applied forces, if any, applied coupling moment, if any, and the body weight if it is not negligible. Sometimes the assumption is we have to neglect the body weight, so we don't mention it, but if it is not negligible, so that we have to mention. So you see the first step, that is isolation. The second, we identify all the loads, that is the mg, that is W, which is acting downward. So then the third step, that is identify all reactions. So the reaction here, that is by the surrounding, and that is the tension T1 and T2. So these are the reactions by its surrounding, that is by both the strings. And the last one, now we have to label the diagram. Label the diagram means we have to mention every dimension, angle, force, and the moment is labeled either a value or a symbolic name if the value is not known. You see here T1, T2 that we don't know. So we have to give some symbol for that. T1 is the tension, this is the first string. T2 is the tension, is the second string. So now we mention the angles also. So now that is the totally labeled diagram. So this is the FBD of this particular case. So these are the steps involved in the free body diagram. Now the support reactions. As we see in the free body diagram, we have to identify the correct support reactions which is given by the surrounding to that body. And when we give the definition of the support reaction, it means that is the support by its surrounding to any body. And now the support reactions always generate in the direction where it can restrain the motion of the body which is externally loaded. So this is very important to give the direction to that support reaction. So that always you have to remember the support reaction is always in that particular direction where it can restrain the motion of that object. If you see this diagram, this block that is placed in this particular floor, the weight of that block, that is W, that is downward, and the block is at rest. It means that is supported by this floor. It means it will get some reaction. So where is that reaction? The reaction is vertically upward. Why? Because that will restrain the motion of that particular block from downward. So that reaction is vertically upward. So that is the way the support reaction generates. If we talk about the covalent force system, and in the covalent force system we have the 3 degrees of freedom. So as per the support we have 3 possible reactions. As per the support it is the vertical reaction force. As per the support it may be horizontal reaction force. As per the support it is a moment reaction. All we have the combination of these 3. So that we have to check in the coming slide how the support reaction will generate according to the type of support. So now we talk about the types of support reactions. So the first one, that is a simple support. Simple support means that particular object will simply rest on the its surrounding. So you see that is the type of this structure. Let us suppose that is a simple beam which is in this particular surface. So that is simply placed on that surface. So that comes in the category of the simple support. And you see the simple support restricts the motion of the body in its perpendicular direction, or here there is a vertical direction. So its reaction is called as a normal reaction. So the support that is vertically upward in this case, because this can restrain the motion of that object in this particular direction only. So we have only one vertical reaction here in the case of the simple support. The second, that is a roller support, and the roller support has again the same tendency as of the simple support, because it also restrains the motion of that object in the perpendicular direction. So here again we have a vertical reaction FV. Okay, so it is also the normal reaction, and the behavior is same as in the case of the simple support. And because the reaction is perpendicular to the surface, so that these reactions are known as normal reaction. Now the third one, that is the hinged or the pin support. You see here, this is the pin, and this is the body which is supported by that pin. So now this hinge support restricts the motion of the body in the horizontal as well as in the vertical direction. So it has 2 horizontal and the vertical reaction force. Now you see one vertical reaction force, that is FV, and the second is the horizontal reaction force, that is FH. So the hinge support can restrain its 2 translation in the vertical direction, the horizontal direction. So we have the 2 reaction forces, horizontal reaction force and the vertical reaction force. Now the third one, that is the fixed support. Now you see, now that particular body is fixed here. So we have the fixed support. This is the fix. You fix it. So when we fix that particular body to its surrounding, then it restricts the motion of the body in horizontal and vertical directions as well as its rotation. Now you can see that all the 3 degrees of freedom in the covalent force system is restrained by the fixed support. So you see, we have one horizontal reaction force, the second is the vertical reaction force, as well as we have the moment reaction. So it means this vertical reaction force will restrain its vertical movement, this horizontal reaction force will restrain its horizontal movement, and this moment reaction will restrain its rotation. So in the case of the fixed support, we have the 2 forces in terms of the reaction forces, horizontal and the vertical, and third reaction, that is in terms of moment. Now the types of loading. So we have the different categories of the loading. The first one, that is the point load. You see here, this is a beam of length L, and the external load that approaches to that body at a point. So that type of the load is known as the point load. It means that is concentrated at a point. That is the point load, P. The second, that is a uniformly distributed load. It comes in the category of the distributed load. Now you see here, so now that load is not at a point, that is spread out in some length. You see, these are the intensity of load. So whenever we talk about the distributed load, so that is given in terms of the load intensity, that is Newton per meter. Now you see in this example, this intensity of load that is constant with respect to its length. So that distributed load is known as uniformly distributed load, UDL. And this small w, which is written above that distributed load, that is known as load intensity. And you see, simple, the height of that arrow will actually the load intensity. And this is the load diagram of that UDL. When we talk about the uniformly varying load, in this category, I discussed the triangular load and the trapezoidal load. Now you see here again, the load is distributed in some length. But now see the intensity. Intensity is maximum here and that is 0 at the other end. And that variation of the intensity, again, that is uniform. So that comes in the category of the varying load. And why it is uniform varying load? Because its intensity varies linearly here, or that is uniformly varies. So it is uniformly varying load. And in this case, this is a like shape like a triangle. So this UVL is known as the triangular load. The second one, that is a trapezoidal load. Again, the intensity is maximum here and that is minimum here, but that is not 0. So this trapezoidal load means it will start with some value and at the other end that is not 0, it again has some value. So that is the shape of a trapezoid. So this is again the UVL because the intensity is varying uniformly, but the shape is like a trapezoid. So this UVL is known as the trapezoidal load. Now the equivalent point load. So whenever we talk about the distributed loads, so it can be modeled as an equivalent point load that is located at the centroid of the object. So when we solve the numericals or the problems of the beam in which the distributed load are acting, so that is a requirement. You have to convert that UDL or the UVL or any distributed loads in the equivalent point load. And equivalent point load is given by the area of the load diagram. So that is the important step. So here what we are doing, we are converting the distributed load into the equivalent point load. So that we are doing. Okay. And for that, the total load is required or the equivalent point load is required, and that is given by the area of the load diagram, and where it will be placed, that will be placed on its centroid. So now the first we talk about the UDL. So you see, this is the UDL. Why it is UDL? Because its intensity is uniform with respect to its length. So this is the load diagram. So if we have to convert that UDL into the equivalent point load, so first we have to find out the equivalent point load. So equivalent point load is calculated by the area of the load diagram. So what is the area of that load diagram? So you see, this is the length L and the height is what? This is W, that is the intensity. So intensity into the length, that is the area of this load diagram, and that will give you the equivalent point load. And where it will placed, it is placed on its centroid. And if it is uniformly distributed load, so definitely its centroid will be at the middle. So the W into L, that is the equivalent point load of that UDL, and that is just at the middle. So that is the distance from one end, that will be L by 2. So that is the way to convert the UDL in terms of the equivalent point load. If it is triangular load, if that is the triangular load, then again the equivalent point load is by the area of this particular distributed load, and the area of this is actually the area of this triangle. So that is half into base into height. So that is half into W into L. The base is L, the height is W, so that is half into L into W or half into W into L. So the area of this load diagram, that will give you the equivalent point load, and where it is placed, that is placed on the centroid, and the centroid of the triangular load you see here. So that is the concept of the centroid. So here in the left side the intensity is maximum. So that you can remember like this. So the centroid of the triangular load is having a distance of 1/3 of the base. L is the base of that triangle, you make it 1/3, and where the intensity is maximum, from there it is the distance of L by 3, 1/3 of the base, and from other side definitely that is 2L by 3. Okay, so now you see this is the triangular load as a UVL, and this is its equivalent point load. Equivalent point load means first we have to find out its equivalent point load value, and then we have to place it on its centroid. And that is the way to convert the triangular load in its equivalent point load. Now at last we take an example of a beam, how we draw a FVD of a beam, and I also talk about how we calculate the support reactions. You see, this is the problem. This is the beam, if you see, and the external load, if you observe the first one, that is a 20 kilonewton meter. What is this? This is the UDL. This is the uniformly distributed. How it is the uniformly distributed load? Because you see the height of the arrow, that is the intensity, that is uniform, that is constant. So this is UDL. Intensity is 20 kilonewton per meter and the length of the UDL is 3 meter. And the second one, that is the point load, that is 50 kilonewton. So one is the UDL, the second is the point load, that is at C. And this beam is supported by a D. What is D? This is the roller support. If you see, the contact is rolling. The second one you see at A, that is a pin. So this is the pin support. So this at A we have the pin. This is the pin support. If you see, this is the pin support, and this is the roller one. This is the roller one. This is the rolling support. This is the rolling one. So now to draw the free body diagram, what is the first step? First you have to isolate that beam. So this is the beam. We isolate that beam from that particular system. And after isolation, the next step is we have to identify all the loads, external load. If you see the external load, 50 kilonewton, that is the point load that we have to act at C. And the second one, that is the weight of that UDL. So to determine the support reactions, now we have the requirement to convert that UDL into the equivalent point load. So to find out the equivalent point load, what is the equivalent point load of that UDL? Its area. Its area is what? 20 is the length, 3 meter is the length, and the height, that is 20 kilonewton per meter. So what is the area of that load diagram? That is 20 into 3. So 20 into 3 is what? That is 60 kilonewton. So this is the total equivalent point load of that UDL, and where it will be placed? That is just at the center. So here see, this is the equivalent point load of 60 kilonewton, and that is just at the middle. So the total length is 3 meter. So this is 1.5 meter. So these are the two applied loads. The first one, that is the point load. The second is the UDL, and that we have to convert into the equivalent point load. Now the support reactions we have to identify. You see, at A we have the hinge support, and already I discussed in the hinge support we have the horizontal reaction and the vertical reaction, because here both the degree of freedom of the translation are restrained by the hinge support. So RAX reaction that restrain its horizontal movement, and this reaction RAY that will restrain its vertical movement. And at the roller support, the reaction is again perpendicular to its surface where the roller is placed, because that can restrain only the translation about that particular direction. So at the roller support we have one reaction vertical, that is RDY, and in the pin support we have the two reactions with respect to A, that is RAX and RAY. So now this is the free body diagram of that beam, and now our objective is to find out these reactions, RAX, RAY and RDY. Now to find out these three reactions, RAX, RAY and RDY, now what we do, we have to use the equations of static equilibrium. So this beam is the example of coplanar force system as a rigid body. So we have the three equations. Net x direction force is 0, net y direction force is 0, and the net moment about any point on that plane is 0, and that point which we are considering, that is A. So that's your choice. So here I make a choice that is about A. Okay. So now first we have to use the equation number 1. So net horizontal force is 0. So first we have to identify the horizontal forces here. So you see how many horizontal forces here in this diagram? We have only RAX. This is the horizontal one. Only RAX. So it means the net horizontal force is 0 and we have only one horizontal force RAX. So RX that is equal to 0. So the horizontal reaction at A at the hinge support, that will be 0. Now the second equation is the net vertical force is 0. Net vertical force, so first we have to identify the vertical forces. If you see the vertical forces, so that is RAY, 60, 50 and this RDY. So how many vertical forces we have? 1, 2, 3 and 4. Now you see the direction. So this RAY, that is upward direction. This is downward. This is downward. This is upward. And now we are saying the net vertical force is 0. So we have to take some sign convention because the directions are opposite to each other. So what we do? We take the upward direction as positive. Upward is positive. And the downward reaction we take negative. Okay, so this sign convention generally we use. So RAY, that is upward, so that is plus RAY. This 60 is downward, so that is minus 60. 50 again, that is downward, so that is minus 50. And RDY is upward, so that is plus RDY. So this is the equation. The net vertical force is 0, that is RAY, minus 60, minus 50, plus RDY is equal to 0. Now we arrange the equation, then we get RAY plus RDY, that is equal to 110. So now our equation is framed. That is equation number 1. Now the third important equation, that is the moment equation. About A, we are taking the moment of all the forces, and definitely that will be 0 because the beam is under equilibrium. So definitely its rotation is also restrained at every point, and here we take that point as a A. So for the moment, again we take the sign convention. The clockwise moment we take positive, and for the anti-clockwise moment we take anti-clockwise moment as negative. Okay, so the moment concept already I discussed in the previous videos. Now we see this is the point. This is the point. I make that point little dark. So this is the point. This is the point which we take. So you have to focus about this point. So now first we identify the forces whose line of action passes through A, because the forces whose line of action passes through A, that will not contribute any moment or will give rotational tendency of that force, that will be 0 because the distance is 0. Now you see RAX, that is already 0, so that is not taken into account, its value is already 0. If you say RAY is passing through A, it means his line of action is passing through A, so definitely that also not contribute any moment. I cross it. Now you see any other force whose line of action will be passing through A? No. So it means about A, the rotation that will be created by this 6 kilonewton, by this 50 kilonewton, and by this RDY. So these three forces will create moment about A, and definitely the net moment that will be 0. So for that, first we have to find out those moment. Okay, so first we pick this 60 kilonewton, this 60 kilonewton. About A, the force is 60. About A, that will give a clockwise rotation about A. So this is plus. And what is the moment? That is the force into the perpendicular distance from that point to the line of action. This is the line of action of this force. This is the point. So what is the distance? That is 1.5. So force is 60. From A, the distance is 1.5. So that will be 60 into 1.5. It is positive because it is clockwise. Next is 50. Again about A, that will rotate clockwise. 50 is the force. Now the distance from A. So now this is the distance. This is the distance. So this is 3 plus 1.5. Again it is positive because that is clockwise. Now the last one, that is RDY. So RDY, that is give anti-clockwise moment about A. You see that will rotate anti-clockwise about A. So we have minus sign here. And what is that moment? That is RDY into the total distance. This total distance. And this total distance is 3 plus 1.5 plus 1. And when you simplify this equation, you get the reaction RDY, that is equal to 57.3 kilonewton. So we get the RDY value, and that RDY value we have to put in the equation number 1. Then we get the value of RAY. So this is the way to determine the support reaction in the case of the beam. Hope this video will be very helpful to all of you. Thank you.